You're welcome to lesson 2, which is devoted in the study of units and dimensions. We have looked at physical quantities and we have to look at units and dimensions. We will start with base units. From base physical quantities, we are looking at their base units. A base unit is any unit which is not defined in terms of other units. It's not defined in terms of other units. This is, that is, it is defined in terms of reproducible physical phenomenon or prototype which does not depend on other units. It's defined in terms of reproducible physical phenomenon or reproducible prototype which does not depend on other units. There are 7 base units defined by international agreement from which other units are derived. So these units are defined by international agreement, science international agreement. What are these units? We have the meter, we have the kilogram, we have the second, we have the ampere, we have the Kelvin, we have the mole, and we have the candela. So there are 7 of them: meter, kilogram, second, ampere, Kelvin, mole, and candela. Now they are also defined. Some are defined they have definitions that we can dabble into. The meter, what is the meter? It is the unit of length defined in terms of the wavelength of light from krypton 86 atom. Now, don't ask me at this level why krypton atom. We said it is an international agreement. They agree that a meter should be the wavelength of light from krypton 86 atom. What did they define? What did they say about the kilogram? It is the unit of a mass defined by an international prototype at France. So if you go to France, you'll certainly see a unit of mass where it was internationally agreed that this should be the standard for a kilogram. The second is also the unit of measurement of time defined in terms of the frequency of light from the calcium 133 atom. So you see, these are all international agreement. It was internationally agreed that a second should be defined as the frequency of light from calcium 133 atom. Now, what is the ampere? It is the unit of current when a force of 2.0 times 10 to the power minus 7 Newton is experienced between two parallel and infinitely long conductors 1 meter apart carrying equal current in a vacuum. Why did I have to actually give this expression? Because now in high school, you are expected to know how to define the ampere by this definition. The ampere is the unit of current when a force of, or is, yeah, is the current produced when a force of 2.0 times 10 to the power minus 7 Newton is experienced between two parallel and infinitely long conductors which are 1 meter apart carrying equal current in a vacuum. What is the Kelvin? The Kelvin is the unit of thermodynamic temperature. The mole, it is the unit of the amount of substance. And the candela is the unit of luminous intensity. All of these came as a result of international agreement. As we've seen those international agreements for the SI unit, let us state what an SI unit is. SI units are internationally agreed systems of units of measurements known as System International. Generally, SI units are used in A-level physics and are founded or built on them. All other units, most units, generally SI units are built on these built on these base units. All SI units, maybe the SI unit of area, the SI unit of velocity, the SI unit of work, is built on this the base SI units that, excuse me, we're going to be looking at. There are also 7 as listed behind, as we saw in our last lesson. We saw the kilogram, we saw the mass, we saw, a kilogram for mass, second for time, ampere for current, the mole for the amount of substance, the candela for luminous intensity, and so on. Even though units are necessary for physical quantities, they also convey meaning. Units are necessary for physical quantities, they also convey meaning. Why do I say so? To say that I have been here for 1 hour is better than to say I have been here for 3,600 seconds. The unit of measurement of time is the second, but it also has higher units, higher values of unit that now make communication applicable or communication palatable, communication meaningful. A physical quantity without a unit has no meaning. For example, if I say my head is 1.9 or my weight is 650, it has no meaning. It has no meaning until units are attached to, which will now tell you the physical quantity that is being measured. We have this table, base quantity, base SI unit and their symbols, mass, kilogram, length, meter, symbol is M, time, second, symbol is S, temperature, Kelvin, symbol is K, current, ampere, symbol is A, amount of substance, mole, symbol is mole, luminous intensity, candela, symbol is CD. And I think we were just a reminder, all of these physical quantities or these SI units that are named after people. Kelvin was a scientist, Ampere is a scientist, Candela is a scientist. I mean, Kelvin and Ampere, beautiful. Their units, the symbols of this unit are capitalized. The symbols of this unit are capitalized. So we have K, capital K for Kelvin, capital A for the ampere, because these were named after scientists. I want us to look at multiples and sub-multiples used with physical or with SI unit. Multiples and sub-multiples used with SI units. We have a prefix, a symbol, and multiple. Deca is 10 to the power 10. Let me just load so we can all go from one to another. We have the deca, 10 to the power 1, hectare, 10 to the power 2, kilo, 10 to the power 3, mega, 10 to the power 6, giga, 10 to the power 9. Others call it giga or giga, 10 to the power 9. Tera, 10 to the power 12. Penta, 10 to the power 15. Hexa, 10 to the power 18. Deci, 10 to the power minus 1. Centi, 10 to the power minus 2. Milli, 10 to the power minus 3. Micro, 10 to the power minus 6. Nano, 10 to the power minus 9. Pico, to minus 12 to the power minus 12. Femto, to the power minus 15. And atto, to the power minus 18. It is good that you know these prefixes, symbols, and their multiples. Now we will look at dimensions. The dimension of a base quantity is a letter representing the physical quantity. In most cases, it is the first letter of the base quantity, usually written in brackets. We look at base quantities and derived quantities. For base quantities, the dimensions is usually the first letter of that quantity and it is written in bracket, mostly capital letters. So we have length as a base quantity, and so its dimension is capital L. Time, base quantity, its dimension is capital T. Let us go ahead. The dimension of a derived quantity is an expression which shows how the physical quantity is related to the fundamental or basic quantity or basic quantities. Now, when we will get to examples, the examples will better drive home this point. Okay. Now, we see base quantity, we see base quantity, dimension, and symbol. Oh, I'm sorry for this distortion. Base, quantity, dimension, and symbol. The mass, the symbol, the dimension of mass is m, and the symbol is m in square bracket. Let it flow, let the chart flow. Length L, time T, temperature K, current A. How do we determine the dimensions of a derived physical quantity? How do we define the dimensions of a derived? How do we determine the dimensions of a derived physical quantity? There are a few steps I would like you to get as we derive the dimensions of a physical quantity. State the formula of the derived physical quantity in terms of its base quantity. Determine its base SI unit. This will help identify its base quantity. Then represent each of the base unit with the dimension of its base quantity. The first thing is to state the formula of the derived quantity in terms of its base quantity. Then you determine the SI unit of the base quantities found in the formula, and you represent each of the base unit with its dimensions. It's very simple. Example, determine the dimensions of the following: area, density, force. We get to start with area. How can we determine the dimensions of area? The first thing we are told to state the formula of area. What's the formula? Length times width. The next thing is to determine the base SI unit. So we are looking at the base SI unit of length and width. Base SI unit of area are m for length multiplied by m for width. The next thing is, now what do? We represent the dimensions of each of the unit. The dimension of this is the dimension of this length is L. Dimension of this other is also L. The dimension, oh sorry, the dimensions of length is the dimension of meter is L. The dimensions of meter is L. So it means we're going to substitute L here and L here. L here and L here. First, state the formula, state the base, state the base unit of the base quantities, then substitute the dimensions of the unit where they are. So if we substitute, what do we have? Therefore, the dimension of area is L for meter times L for meter, giving us L squared. So area is length times width, base unit of area. The unit of length is m, the unit of width is m, and the dimension of meter is L, which is the dimension of the physical quantity. We use the dimension of the physical quantity for also as the dimension of the SI unit. So if we now substitute in the place of L, we are substituting bracket L in bracket in the place of m, and this L in bracket again, square bracket in the place of m. So we will have L times L, which will give us L squared. Next, density. State the formula: mass divided by volume. State the base unit: kilogram per meter cube, which is translated as kilogram meter to the power minus 3. Now, one thing that you should catch your attention is this. In high school, we no longer represent unit with slashes like kilogram slash meter cube. No. In the high school, we no longer represent unit as kilogram slash meter cube. No. It is kilogram meter to the power minus 3. Kilogram meter to the power minus 3. So meter per second is no longer going to be meter slash second, but it is going to be meter times second to the power minus 1. Take that as a lower seed student. The dimension of kilogram is m. Kilogram is for mass, so the dimension of kilogram is m. We represent the dimension of the quantity. We represent the dimension of the SI unit with the dimension of the base quantity. Kilogram is from mass, and the dimension of mass is m. So we will represent also meter is from length, and the dimension of length is L. So that's what we're going to have. Dimension of meter is L. So in the place of kilogram, we're going to substitute m, and in the place of mass, in the place of meter, we're going to substitute L. What shall we have? We shall have m L power minus 3. Don't write m slash L to the power 3. No, this is meter, mass per volume. Mass per volume. This is mass per volume. It's getting interesting. You see, dimensions. Okay. Force. State the formula of force is equal to mass times acceleration. But since we have to express them in terms of their base quantities, we must also break down acceleration. But the time comes when you will immediately know what acceleration is. You will immediately know what the dimension of acceleration is. You might not need to break it down. As you are going, as you are solving problems, it will become just normal for you to use them. The base unit are kilogram meter per second square. Kilogram for mass, meter per second square for acceleration. This is what it is. But since we are now in high school, we will no longer use this slash. We're going to represent it with s to the power minus 2. So this is kilogram meter per second square. Kilogram meter per second square. So we are going to we are going to identify the dimensions associated or attached to kilogram, which is m, the dimension attached to meter, which is L, the dimension associated or attached to second, which is T. We said we're going to use the dimension of the physical quantity from this kilogram. I know that it is this is the SI unit of mass. And what is the dimension of mass? M. From here, I know this is meter. Meter is the SI unit of length. What is the dimension of length? L. Second, the second is the SI unit of time. What is the dimension of time? T. Remember, I said most of the base quantities have the first letter as the dimension. There's a table for dimensions that you will see all the physical quantities and their dimensions. So if we substitute kilogram with mass, with m in bracket, we substitute meter with L in square bracket, we substitute second square with T in square bracket, we're going to have this mLT to the power minus 2. So this is the dimension of force, mLT to the power minus 2. Okay, now this is the table. We have quantity, definition, how they are defined, SI unit, and dimension. Area, length times width, SI unit is m squared. Dimension, L to the power 2. Volume, length times width times height, m cubed, L to the power 3. Once you know these SI units, you'll be able to identify or associate the dimension of the base quantity it represents. Now you have to study this. This is acceleration. There is no acceleration is displacement on time square. Velocity is displacement. This is displacement on time. Force is mass times displacement on time square. Momentum is mass times displacement on time. Pressure is force on area. Charge is current times time. Work is force times distance. Voltage is work done per unit charge. Work done on charge. Capacitance is charge on voltage. And these are their SI unit and the dimensions. This does it for lesson number 2, and we are moving forward and advancing. So it is time for you to go over it and make yourself comfortable. You can study it at the comfort of your home, and at every time you find good or convenient. That is why we have these lessons online. So you will not be compelled, but you can discipline yourself. That even at, you can get up in the night, you can have your classes on Sunday, you can have your classes, or even in the morning, you can still have your classes at whatever time. This kind of arrangement is going to really work for those who want to study and yet they cannot be found in a formal classroom. Thank you. See you. Don't forget to subscribe, click the notification button, and share. You are on to Asanji Academy for Global Conquest.